I think we can start now. Hello everyone. I'm Kafe Abzarva from SPE BHOS team. I will be your moderator for this session. As you remember, last time our speaker, Sanan Bey, talked about all refinery processes, but some parts are still remaining, and today he will continue and end his presentation. And additionally, we will have a quiz which is prepared by our dear speaker, Sanan Bey. And the winner of the quiz will get a present from our speaker. So just stay until the end and compete and get your present from our speaker. Now I am leaving stage to you. And if you have any questions, you can just unmute yourself and ask, or you can write in the chat box, and so that Sanan Bey will answer to your questions. Please, Sanan Bey, start.
Thank you, Kafiye Hanım, for the introduction. This is the third session of the oil refiner processes. Still, 3 sessions are not enough for such huge process, but I will try to summarize the most important parts of the processes at the oil refinery. So again, the same thing, how we learn, I have to repeat it each time so that everyone can use it. Instead of memorizing, engineers think, analyze, and understand what you are reading, listening, or seeing, and this way they can learn. And after learning, it is always important to repeat, reproduce. Repeat can be that repeating your notes, reproducing can be that the tasks or assignments, homework, or teaching others. So teaching or sharing your knowledge with others is always the best way of the remembering. So I have to mention that I use the slides from the petroleum refining course on Udemy platform. And for those who are interested, they can go to this course. This is not an advertisement, but I use the slides from them. That's why I have to mention it. So we started from the oil refiner block flow diagram. This is the block flow diagram. You are seeing from the first session. One moment, my pen is not working. Yes. So what we said, we have crude oil. Okay, now it's working. We have a crude oil and we have crude oil which comes to the CDU unit. The CDU unit was the topic of the last session. And then from CDU, we produce the main products: gas, naphtha, kerosene, diesel oil, and atmospheric gas oil. And then the atmospheric residue, we call it AR, is sent to vacuum distillation unit, VDU, which we talked about the last session as well, but we couldn't finish it. And then from vacuum distillation unit, we have the VGO, vacuum gas oil, light and heavy. These are sent to the first hydrotreater, and then FCC unit, catalytic cracking. So today we will talk about the hydrocracker. Today we will talk about the catalytic reformer, so where the heavy naphtha is converted to the reformate. And today we will also talk about the hydrotreating processes in general, which can be the naphtha hydrotreater, which can be the diesel hydrotreater, which can be the VGO HD. So VGO is feed, that's why it's called the VGO HD hydrotreater. We have also hydrotreater here, which is called the FCC gasoline GHT, gasoline hydrotreater. In fact, we don't need 2 hydrotreaters here. So either we have the feed hydrotreater or we have the product hydrotreater. In general, we don't use 2 hydrotreaters, both for the feed and the product. And we have also hydrocracker unit here. So if we have FCC, we mostly don't have the hydrocracker. In this case, the light and heavy gas oil is sent to FCC, not here, but to FCC unit. So today we will talk about the vacuum distillation unit, fluid catalytic cracking, continuous catalytic reformer, and hydrotreating units. So in the previous session, we talked about the CDU, crude desalting, heat exchanger network, stabilizer section. Today we will continue with the vacuum distillation column and other units. So vacuum distillation column here, this is CDU. You can see that it is thinner and higher compared to VDU. But VDU has a bigger diameter, but it is shorter. And this is, which I will talk about later, the vacuum creation, the pipelines, where the ejectors are used. So vacuum video overview that you know that AR, atmospheric residue, is sent to VDU unit. And here we recover a small portion of diesel which is left in the atmospheric residue. We have the light vacuum gas oil. We have heavy vacuum gas oil. These are sent to FCC. And we have the atmospheric vacuum residue, which is sent to DCU, delayed coker unit, and BBU, bitumen blowing unit. So last session, I wrote the long definitions. I assume that you already know the abbreviations. That's why I will tell them the long names, but write down the abbreviations in order to save time. So pressure is nearly vacuum. That's why it's called the vacuum distillation column. From 25 to 40 mmHg, and we know that 1 atm is 600 and 760 mmHg. In this case, this is referred to around 0.05 atm, or you can also use the bar G. The height is between 12 and 15 meters. In this case, the CDU height is above 20 meters. So the raw material is AR, like atmospheric residue. We have the pump here. We have the preheating heat exchanger. We have furnace here. We have to heat it around above 400 degrees Celsius. And then this is the vacuum distillation column, where we can see that we have the vacuum gas oil product, vacuum gas oil. So this is it is heavy vacuum gas oil. Actually, I think, okay, this is not heavy, this is light, sorry. This is the light vacuum gas oil. We have the heavy vacuum gas oil here. And then these are the ejectors, which I want to talk about more later. We use the ejectors to create a vacuum in the distillation column. And pump around, this is the pump around. This is the pump around, which we talked in the previous session, that we use the pump arounds to control the temperature at certain points or the trace of the column. Vacuum distillation unit operation, you see that we have the heat exchange zone, we have a flash zone, which is here. Heat exchange zone are the sprays, we have the special packing, and we have trays. So in video, we might have packing plus trays, or in video, we might have only packing, but in CDU, crude distillation, we have only trays. One of the differences between the VDU and CDU. Here, you can see that light vacuum gas oil pump around, heavy vacuum gas oil pump around, light vacuum gas oil product, and heavy vacuum. So this is the mixed product. This is HVGO product. This is the LVGO product. This is the mixed VGO product. Then we have the slope oil, which mostly is recycled back to the crude distillation unit. And then we have the vacuum residue, where we send the vacuum residue to delayed coker unit to produce coke, and bitumen blowing unit to produce bitumen or asphaltene. This is the simplified PFD. Again, you see the heaviest from atmospheric distillation column. We add the steam here in order to decrease the viscosity, which was the question given in the previous session, that AR has the higher viscosity. How we pump it in the pipelines. To make it easier, we use steam. We have the preheating, and then furnace is not shown here. Again, the same products, VGO is sent to FCC, and we have the ejectors here. Let's talk about the ejectors. What are the ejectors? Ejectors are the vacuum creating system. We use the steam. You can see motive steam. It can also be changed to diesel. The diesel product from the vacuum column. It depends on the process. So it is decided in the design stage. And then you can see that we have two ejectors here, 1 and 2, and we have pump here. Pump is pumps the liquid with a high flow rate and higher speed, and then it goes into the ejectors. Here you have the venturi tube. You know that this is the this is the venturi tube, and where we can apply the Bernoulli's equation. And once it comes here, the velocity becomes higher and pressure becomes lower. And as assume this is your VDU, you have the P2 and P1 here. When P is bigger than P1, the air in the VDU moves upwards from higher pressure to lower pressure. This you can create the nearly vacuum condition, which is 2550 mmHg here. So this is the ejector. The main part to create the vacuum is the venturi tube part, and then afterwards the steam and air is sent to the silencer, because it creates the sound. You know from the vacuum cleaner in your house that creating vacuum condition costs sound. And then we send it to the separator. This is the separator to separate the air and liquid, gas and liquid. I will send the slides to you. You can click this video and learn ejector working principle more. So that's about the video. Now let's go to the next unit at the refinery, which is the catalytic cracking unit. We will talk about the overview of the processes, chemistry of the process, and process description of the process. Before starting FCC, I would like to ask you if you have any questions.
I have a question, yes.
Yes, please.
Could you please go back to the slide VDU overview, previous slide? Just a second. Not this one. It was written, previous than VDU. This one. Yes, it was written that the few millimeters decrease in pressure drop between vacuum inducing device.
Yes.
The next one. It will save costs. How will it save costs? I mean, I didn't understand how we will create the pressure drop and where it will be placed.
A few millimeters decrease in pressure drop between the vacuum inducing device and the flash zone. So the vacuum inducing device is this one. Here we have the vacuum inducing device is the ejector. So we have the ejector here. Okay. So between top part and the flash zone. Where is the flash zone? You see the bottom part. So
yes,
bottom part. So more pressure drop you have, you lose more energy. That's why. But pressure drop comes from this packing trays, sprays, packing from this section, from inside internals of the column. It means that you always have a limitation to pressure drop. Once you see that the exceeds the limit, the maximum limit of pressure drop, you start to investigate where it comes from. Maybe you have caulking inside the packing, or maybe you have some problems with sprays. Often the trays can move in the column. So then so all these problems are noted, and once the plant is shut down, you check all of them in the column and see what the problem is. But if the pressure drop becomes really higher and higher, it means that you cannot operate anymore. You have to shut down the unplanned shutdown and see what the problem is.
Okay, yes, it's clear. And one more thing,
Sure.
what's quenching oil? Then on the next slide.
Where it was.
No, it was in the before. I believe. Just a second. It was quenching oil, wash oil. That same slide. Yes, here.
So
The
quenching
stripping
means quenching means also cooling. So you see that we have the hot vacuum residue, hot, and we have a pump, we have heat exchanger or steam generator. So the heat is given from VR to water to create the steam. And we have the cooler, water cooler, and then we have air cooler. So we have cold vacuum residue. And then some part of the not vacuum gas oil, sorry, can be sent back to the vacuum column for cooling. So as I said, it plays a role of the pump around. You use this one to control the temperature at this point.
It's clear. Thank you very much.
Yes, the washer is also the same to control the quality of vacuum gas oil. If you see that there is some problems in terms of the boiling point or other parameters, you play with the amount of wash oil which is sent back to the column. However, you always try to keep the wash oil or reflex or the quenching oil, the flow rate as minimum, because increasing the because increasing the flow rates, recycling back to the column, increases your furnace duty, so increases the costs. So is it clear?
Yes, it's clear. Thank you very much.
Thank you for the question. Now I will continue with the fluid catalytic cracking. From distillation column, we have the VGO here. And what we said that from the VGO, LVGO, light vacuum gas oil, and HVGO, heavy vacuum gas oil mix, VGO is sent to first hydrotreating, which I will talk about later, and then the catalytic cracking we will call FCC. So fluidized catalytic cracking. So this is FCC, as you can see the where it is located in the BFD. The overview. The overview process is that we have the, but before starting this one, CDU and VDU is separation based on the boiling point. That's why it is physical processes. However, we will talk about FCC, CCR, hydrotreating. These are the chemical reactions. Chemical processes, sorry. And we will see that if you have a chemical process, it means we have a reactor. And we will see that the reactor for each type of the process is different from each other. And that is for me, one of the beautiful sides of the refinery, that you have different units. You have the reactor different in each unit. You have the distillation column or the stabilizer different in each unit. Coming back to FCC, we have the raw oil charge, which is VGO, is sent to reactor, and we have the regenerator where the catalyst is regenerated, and then all the product leaves from here, which is sent to fractionator where we separate gases, gasoline, light gas oil or light cycle oil, which can be LCO and HCO. LCO is diesel, HCO is sent to DCU to produce coke. So the unit is one of the most important units of the modern refinery. Why? Because it produces the gasoline, and this adds the essential value to the refinery. Feedstock products, we talked about this one, and here you can see that the reactor, the tallest one is the reactor, and you have the regenerator here, and you have the main column, stabilizing column. So reactor, regenerator, stabilizing or fractionation column. And the products, these are the products, the light gases C1, C2 and H2, LPG, C3, C4, gasoline C5, light cycle oil, which is also diesel, heavy cycle oil sent to DCU, that's the heavier fraction, clarified oil or decant oil or slurry, this BHOS is sent to DCU to produce coke. So we have to mention that straight from gasoline or straight run naphtha. What is straight run? Straight run means that coming from CDU VDU. Straight run kerosene, straight run gas oil, straight run naphtha. Straight run naphtha has octane number of the 40 to 60, but we need the above 92 or 95. That's why straight naphtha, so we have light naphtha, which is sent to isome, and then the product from isome has octane number of 87.5. Heavy naphtha is sent to CCR. We will talk about CCR today. So isomerization is here, and CCR, what is it? CCR, naphtha catalytic, CCR is here, and CCR has an octane number of the 95, 100, and then from VGO we have it is sent to FCC. From FCC we have the FCC gasoline, which has an octane number of 92, and we have the MTB product, which is added directly to the gasoline pool, has the octane number of 115, 120, and then these are all sent to gasoline pool. As you can see here, in China, the FCC gasoline has the most contribution to the gasoline pool. And I told you we have the gasoline from cracking, reforming, and isomerization. Typically, cracking involves thermal and catalytic. Who can tell me what can be the main difference between these decompositions, thermal and catalytic? In idea. So, okay, I will ask the question differently. Why we don't want to use the thermal, but we want to use the catalytic decomposition?
Maybe thermal decomposition will damage to the composition.
Thank you for your answer, because you said just your idea. It is also important. But however, the correct answer will be that in thermal decomposition, we have the higher temperature. And in catalytic decomposition, temperature is not low temperature, but lower compared to the thermal composition. For instance, we can have the 600 Celsius here, but we can have the 500 Celsius here with the help of the catalyst. And the catalyst, what is the role of catalyst? It helps to decrease activate energy. So if you don't have catalyst, of course, activation energy will be higher. We have to use more energy, more fuel, etc. But when we use a catalyst, the activation energy decreases, but we have to deal with the catalyst. That's why we will have the regeneration for the catalyst. And in the regeneration side, regeneration side, we will use one of these few products, let's say, as fuel. It can be fuel oil, kind of diesel, fuel gas, or natural gas. Fuel gas is produced in the refinery. So it is a C1, C2, both of them C1 and C2. But the fuel gas produced in the refinery. But if you don't have enough fuel gas, you purchase natural gas from outside. So that's the main difference between fuel gas and natural gas. I check the time to time, not to exceed my allowed time for presentation. So FCC overview is that it is carried with, when cracking is carried without a catalyst, higher operating temperatures and pressures are required. So when you have the higher temperature, higher pressure, your capex means the capital costs. The costs to construct let's say the reactor or regenerator for higher temperature and pressure becomes higher. But nowadays all the processes are with catalyst, the FCC chemistry. So it's a gas phase reaction, because it is still high temperature reaction. And the residence time, what is the residence time? Which one? This is the reactor, I think. Yes, this is the reactor. So residence time means that if this is a reactor, until this part, you have 1 to 3 seconds. So it is fast reaction. In 3 seconds, the cracking is accomplished, and you produce the gases, naphtha, or light cycle oil. As you can see, the catalytic cracking is in low pressure, still high temperature process. 480 is, I think, lower. In our refinery, it is a bit higher than 500. But still, we are saving the high amount of pressure just using the catalyst. FCC chemistry. I added too many slides regarding the chemistry. If you have time, you can just check later. The important part is that we use the zeolites as a catalyst to FCC. So in the reactor, we have the cracking reaction, isomerization, the hydrogenation, hydrogen transfer, and so on. There are thousands of different reactions occur in the FCC. And what I want to say that paraffins, these are the alkanes, olefin, but with at least having the 9 carbon atoms. Olefins, alkenes. The naphthens, the cycloalkanes. The aromatics, you know the aromatics. And here you can see that what types of reaction goes with each type of the hydrocarbon. One of the things that I want to add that you might see PONA analysis for the, let's say, the VGO and different products in the refinery. The PONA stands for the paraffin, olefin, naphthalene, and aromatics. This PONA analysis, you have the result of each type of the hydrocarbon in your sample. Process description. So this is kind of the block flow diagram of FCC process. This is the reaction. This is actually one column. So this is actually one column, I think. Yes. We have the regenerator. And we have the fractionator. What we do, reaction, it is obvious. We have reaction here. And the reaction vapors are sent to the fractionator where we separate the gas, LPG, what is LPG? C3, C4, gasoline, and I think this is the water, light cycle oil, LCO, this is diesel product, and the fuel oil. So what we can do with fuel oil, we can burn it if we need. So the same, we have the distillation column, regenerator, stabilization of naphtha. And we have 3 main sections, as I told you before: reaction, regeneration, and fractionation. So I will explain the process here. So FCC reactor, feed enters the cracking reactor, and this is the riser reactor. FCC reactor, we call it also riser reactor. And this is your feed, which is VGO feed, and here catalyst plus VGO meet. They meet at this point, and this catalyst has a temperature of the 700 degrees Celsius, and the feed has a temperature of the 300 degrees Celsius. And of course, when they meet, the total temperature becomes the 500 plus, and then all the VGO is evaporizing, and evaporation and the reaction goes immediately. And with the help of the catalyst, you have 1 to 3 second residence time in the riser reactor from here to this part where the reaction goes on, and then all the VGO is cracked. Nafta stabilization. So once you before Nafta stabilization, I will talk about the product separation. So you have the product here, the gases, which are sent to fractionation. Here we separate the gases, naphtha, gasoline, and LCO, HCO. HCO, some of them can be recycled back to the reactor, or it can be sent to DCU, delayed coker unit, to produce the coke. In the regenerator, what happens in the regenerator? So catalyst goes from the reactor to the regenerator, and we have here air. And catalyst has some coke. Coke is the deposited, let's say, the hydrocarbon on the catalyst. And we add the air. We have the coke and air, and we burn it. So we burn the coke. That's why the burned coke leaves as the flue gases. And then after it is separated from the catalyst particles, it is sent to atmosphere. But we burn the coke, and then the regenerated catalyst here goes back to the reactor. That's why it is called the fluidized. So your catalyst moves like a fluid in the reactor regenerator, like this. Is it later? Later, okay. Then we have the Nafta stabilization. So where we have the unstabilized naphtha. Unstabilized naphtha means that naphtha plus gases in the coming stream. And here we want to separate the gases and naphtha. That's what is what means the stabilization of the unstabilized naphtha main column. And the gases later is cleaned with the amine, and then is sent to or the refinery, or is used as a refinery fuel gas, or they can be sent to flare. And then here you have the liquid product, and then you have the stripper. What does a stripper do? Stripper separates the gases and LPG. What's LPG? C3 and C4. And after LPG, the stripper separates the naphtha plus LPG, and which is C3 and C4, and the gases is separated, which is sent to the separator, and then gases is sent to primary absorber. Here we have the debutanizer. Debutanizer separates the stable naphtha. You can see that we have stable naphtha here, and LPG here. LPG is C3, C4. And then we have the depropanizer, where the propanizer separates the C4 and C3. Now we have the PPF, propane propylene fraction, and BBF, butane butylene fraction here. The overhead gases is sent to compressor, and they are sent to primary absorber and the secondary absorber. As I told you, that here we have the lean oil or lean amine to treat the gases. This is the secondary processes in the refinery. I talked about the stripper, and I talked about the propanizer. Okay, here it is again explained that we have a riser reactor. In the riser, this is the long tube where we have the reaction. The feed is allowed to get into contact with the hot catalyst, and the hot catalyst is enabled to rise through lift media in the riser. You can also call it lift reactor. And then cyclones. Who has an idea why we need cyclones? What are the cyclones used for?
I have an idea, but I'm not sure.
Yes, you can share your
You mean
ideas.
hydrocyclones, yes?
So kind of say your idea.
Okay. If I don't mistake, they are also used in they are one type of the separation processes that we use in the process equipment. They are mainly used for the microparticles. I mean, the separation processes are based on the size of the particles. That's why for the micro ones, we use hydrocyclones.
Yes, it is correct. Thank you. Okay. So cyclones is used to separate the catalyst microparticles, catalyst particles from the gases. So what happens here? The gases enters here and here. Here you have the cyclone, and with the help of the merkezden kaçma güvvesi. I forgot its name. And with this, the physical law, we can separate the catalyst. They go back to the, let's say, the reactor down, and reactor product in this case leaves from top. This is for reactor part. But we have also cyclones in regenerator. Here again the same. The gases inlet is here, and then the flue gas leaves the regenerator, and the catalyst goes back to the regenerator. So using the cyclones, we do not allow the catalyst particles leave the reactor in the product stream or leave the regenerator in flue gases. So you have the controllers here. So with this one, you control the flow of the catalyst from regenerator to reactor. So it is the strange that you control the temperature, this one. So who can tell me how you can control the temperature in the reactor with this control valve?
By sending enough fluid, I mean.
What do you mean by enough fluid?
I think the fluid temperature can be different, and by sending this fluid, it can affect our temperature.
Yes, I think kind of. The exact answer, thank you for your answer, and thank you for sharing your ideas. The exact answer is that the lifts, so we have the feed, which I said comes around 300 degrees Celsius. And we have the catalyst here coming at 700 degrees Celsius. So we heat the feed with the catalyst. If, let's say, we see that the temperature is below 500 degrees Celsius, we have to increase it. Then we open this control valve a bit more, allowing more catalyst coming into the reactor. Thus, we can control the temperature. If the temperature, let's say, is above the 120 Celsius, then we close the control valve a bit, allowing the temperature to decrease. And this one is pressure controller. Control the pressure at the top. How? Because we have the catalyst here with coke. Coke is burned. When the coke is burned, the flue gases are formed, and the flue gases create the pressure. There is a lower pressure limit above, which also controls the temperature. That's how this control valve is used. And air. We use the air, as I told you before, to burn the coke deposited on the catalyst. We have again the cyclones here, and the cyclone separates the flue gases and catalyst, and the catalyst is solid catalyst goes back to the reactor. This is all about the FCC process. Just summarizing, we have the reaction part, we have the catalyst regeneration part, which is the one column, and then we have the fractionation part, where we separate the products, which are the gases, which naphtha or FCC gasoline, LCO, and HCO. Light cycle gas oil, this is a diesel product, and HCO, and slurry. HCO and slurry are the heavier products which are sent to the late coker unit, where we produce coke. And another important parameter is conversion here. How we find the conversion? So the amount of gases plus naphtha plus LCO divided by the VGO. This is your feed. This is your conversion. So we can say that HCO and slurry unconverted products. You might expect of the conversion around 0.87. So this was about the FCC. Now we have the catalytic reformer. So the vacuum distillation, we said that if we don't have hydrocracker, this is also sent here to FCC hydrotreater, then the FCC. But we have the heavy naphtha. Heavy naphtha is sent to hydrotreater, and the hydrotreated heavy naphtha is sent to catalytic reformer to produce the reformate. Why? Because the reformate has an octane number of the 95,100. Deforming in which the low octane gasolines will form the high octane gasolines via chemical reactions. Heavy naphtha is our feedstock, and it produces the light ends, reformer gas H2. So this reformer is the main unit producing the hydrogen in the refinery. Then after the calculation how much hydrogen is produced in the reformer, another secondary unit, HPU, hydrogen production unit, is constructed. So it is only for hydrogen production, but we accept the hydrogen production unit, CCR, or catalytic reforming, is the only unit that produces the hydrogen in the refinery. This is the overview of the process. As you can see, we have the paraffins from 30 to 70. In the products, we have the 30 to 50. We mostly convert naphthenes, cycloalkanes to aromatics. So aromatics contribute to research RON number, octane number. We can say that the reforming is used to produce the aromatics, or to convert the naphthenes to aromatics in the heavy naphtha product. The operating conditions can be between the 1 to 45 atm pressure and around 500-520 degrees Celsius. Catalytic reforming, C7-CHON hydrocarbons with low octane numbers are converted to aromatics and isoparaffins which have the higher octane number. So the process will rearrange and restructure of the hydrocarbon molecules, breaks some of the molecules into smaller molecules. High temperature reactions, always involve cracking. We only want cracking in FCC. We don't want cracking in other units. However, we cannot avoid it. If there's a high temperature, then obviously there will be some cracking. And what happens when there is cracking? Gas is formed, and gas acts like a coke on the catalyst. And as I told you, hydrogen is produced in CCR. So this I showed you in the first session. So we have the RON, which is also in the second session, research octane number, and we have MON, which is the motor octane number. Different ways to measure the octane number of the naphtha or gasoline products. There is a difference of 10. For instance, if the RON is not always 10, but around 10. If RON is 95, then MON will be 85. This is, I think, in the USA, where while selling the gasoline, they don't show the RON. So in the gas stations in Azerbaijan, we show the research octane number. But here they show the research plus motor divided by 2. So for this one, RON is 92, RON is 95, RON is 98. So here you can see the octane number of the different molecules, such as M-butane, 94, and M-pentane. This is the really low. That's why you want to avoid the M-pentane in your product, but isopentane has higher octane number. And also you can see that the branched or iso-alkanes or hydrocarbons have higher octane number compared to the normal, those straight chains. So chemistry, you have of course, the desirable reactions and non-desirable reactions. Desirable reactions are the dehydrogenation of naphthanes to aromatics, because aromatics is the main product you want to produce. Here you can see that the naphthanes to aromatics, conversion of paraffins to naphthanes. So paraffins to naphthanes, naphthanes to aromatics, olefins to paraffins, and the hydrocyclization of paraffins to aromatics. These are the desirable reactions. You have also the non-desirable reactions, such as the dealkylation, hydrocracking, etc. These are the reactions mechanism. I will skip this one. And I added this slide so that you can check them later, but I want to skip these slides. I want to talk about the process more. But if you have any questions, please ask me regarding the reactions, or in other slides I already talked before. Here we have the naphthalene dehydrogenation reactions, paraffin hydrocyclization, and favorable condition. It is important always to control hydrogen to feed into the reactor. So I will talk about later in the process. These are the chemistry and favorable conditions for these reactions. Linear paraffin isomerization, favorable conditions for paraffin dehydrocyclization. And naphthanes isomerization, and undesirable reactions. As I told you, hydrocracking is one of the, and the coking are one of the are the main undesired reactions which happens in the both reforming, also in hydrotreating. Coking, actually this is coke, but the coke as a product which is produced in DCU. DCU to produce coke. And coke is burned in the furnaces, where you want to achieve the around 800, 1000 degrees Celsius. But when there is the coke deposit in catalyst, of course it is not like that, but assume this is your catalyst, coke starts to deposit on your catalyst. And when it is deposited on the catalyst, first it deactivates the catalyst, and secondly it can create some other problems. For instance, what we said that by regeneration we add air and burn the deposit catalyst. The catalytic reform process description. So first we have the feed preparation. We have the naphtha hydrotreatment. Here we use the heavy naphtha, and it is sent to hydrotreatment. Hydrotreated heavy naphtha is sent to the reactor. Why we hydrotreat it? Because the catalyst is so sensitive to sulfur content. We don't want sulfur in the reforming feed because it poisons the catalyst. And then we have the preheating, and we have the temperature control, and we have the reaction. Reforming process is the endothermic process. That's why we have a few stages of the reactor and furnaces. For instance, you have the feed here. So you have the feed here coming to the reactor, and then it is sent back to the furnace. It is heated further and sent back to the furnace again. Mostly it's around the 520 degrees Celsius at the inlet of the reaction, and you have the third reactor. And then of course it's the same for all plants or units. You always have the product separation after the reactions. So you have the product separation, which we call the stabilizer. The product is the reformate, and then from top you the gases leave from top, where you cool it down. When you cool it down, you get the C3, C4, LPG in a liquid phase, and gases are C1, C2, which are sent to refinery fuel gas the system. The common process in industry, we have the three types of the catalytic reforming. So the first one is the semi-regenerative catalytic reforming. As you can see, not totally regenerative, but semi-regenerative. We have a few reactors here. So what we do, we take the catalyst out of the process, to regenerate it separately from the process, and then we add it back to the process. So then we have the cyclic catalytic reforming, which so this is a cyclic catalytic reactor. So where you can see that we take the catalyst out, and then we take the catalyst out from the system, but we do it continuously, which is different from the semi-regenerative catalytic reforming. But the most commonly used is the continuous catalytic reforming, CCR. As you can see, the catalyst is recirculated in between the regeneration section and the reaction section. These are the three reactors on top of each other. But it is essential to note that in FCC, we have the one column, regeneration column. But here we have the CCR, we have the regeneration section. So this is not just one equipment. Here you have the, let's say, the heat exchangers, you have pumps, etc. It's a separate system, but that is connected to the main process. That's why it's called the continuous catalytic reforming. Okay, talking about the process description, we have feed. What is our feed? It is heavy naphtha. Hydrotreated heavy naphtha is our feed. It is sent to the reactor. Here the reactors are shown like this one, but mostly it is like this one. You have the reactor on top of each other. You might have 3 reactors or 4 reactors. The heavy naphtha is sent to the furnace, and you have the hydrogen recycle. You can ask that we produce the hydrogen in CCR. Why we have the hydrogen feed into the feed? Because we have also the hydrogenation reactions in the reactor. That's why what we do, we add the feed plus H2 to the reactor. And from reactors, we have the products and H2. Some of this H2 is recycled back to the inlet, and the rest are sent to hydrotreating process. This is the main process where we use the hydrogen. Hydrotreating process. I will talk about hydrotreating later. So this is the reaction section where you might have the 3 furnaces and 3 reactors, or 4 furnaces, 4 reactors. And then you have the final heat exchanger where you cool down your product, and this can be done with preheating your feed. So let's say this and this one can be the same heat exchanger. How it works? You have feed, you heat the feed which goes to the furnace, and this is your product. This is your product. You cool down your product which goes to separator. Here you have the separator. You separate the gases from the product, and gases mainly are the hydrogen gases are sent to the compressor and back to the feed, or to the other units such as the hydrotreating units. And your product is sent to, it's not debutanized, yeah, I will call it stabilizer. Stabilizer, where you stabilize the reformate having the 95-100 research octane number, and then you separate the gases from C3 and C4. And you have the regeneration section, which is the different from the main process, but it is connected to the process. So here you can see that we have the regeneration. Okay, this part we have the feed cycle unstable. We don't have shown the regeneration here. In this reformer, the catalyst is in moving bed and regenerated frequently. This allows operation at much lower pressure with a resulting higher product octane. This type of the reformers are radial flow and are either separated as in regenerative unit or stacked one above other. So I will ask you why we need the continuous reforming. What would be if we don't have continuous reforming? Not reforming, continuous regeneration. Sorry. What's the advantage of continuous regeneration? Any idea? So assume we don't have the regeneration here. So we have only the catalyst and reactors. What happens as time passes? There's reaction here. When there's reaction, the catalyst can be poisoned with, let's say, the sulfur. Can you hear me?
Yes.
Okay, because we have the electricity gun at home. That's why I wanted to ask you. It can be poisoned with catalyst or it is deactivated. So if you don't have regeneration, that's also the same for, let's say, FCC. If you don't have regeneration, then the reaction, the desired reactions rate start to decrease. So rate decreases because the catalyst is deactivated. And once it's reached a specific point, we have to stop the process. We have to take the catalyst out. We have to reactivate it and put back to the system. But this is additional cost. Every time the refinery shutdowns, that's the cost for the refinery, because the shutdown and the startup is additional cost, first of all, and the secondly, during the time you don't operate, you don't produce product. It means you don't earn money. So to prevent the refinery shutting down, or not the refinery, at least the unit shutting down, you have the catalyst regeneration system, which is connected to the main operation system. So summarizing, you have heavy naphtha feed, and then you have the gas product C1, C2, which is burned. You have the LPG C3, C4, and you have reformate, which has the 95, 100 research octane number. What is the first product you have from CCR? What's the first product? What we'll use in hydrotreating? No one has an idea. What is the first product? What do you see in this slide?
Maybe hydrogen.
Yes, exactly. Thank you. The first product is the hydrogen. So hydrogen is only produced in CCR, in the refinery. There is no other unit that you produce hydrogen. Of course, you have HPU, hydrogen production unit. And why we need hydrogen?
As you said, in hydrotreating process, we'll use hydrogen.
Yes, exactly.
In the hydrogenation
process. I will go back to this. So you can see that heat plus H2 goes to reactor. We have the products, and we have the H2 is also a product. Some of them is recycled back to the CCR process, and the rest are sent to hydrotreating process. And we have additional hydrogen comes from HPU, hydrogen production unit. So we talked about the CDU, we talked about the VDU, we talked about the catalytic reformer, we talked about the FCC. Now I will talk about the hydrotreating processes, which is must for all the refiners. You cannot find any other refiner without a hydrotreating process. And why we need the hydrotreating process? To clean. clean impurities, such as we will see which impurities later. Sometimes you can use the kerosene hydrotreater, but mostly recently the Merox treater are used for kerosene. That's why we don't have kerosene hydrotreater in this scheme. So what are the Merox? You use the caustic plus amine to clean the impurities in the kerosene. So this is physical process. But hydrotreating process is chemical process. Chemical process means that we have the catalyst and we have the reactor. Hydrotreating process. What are the impurities we want to treat in this process? The sulfur, which can show itself as a mercaptan, sulfide, disulfides, polysulfide, thiophenes, etc. And thiophenes are most difficult to eliminate than most of other types of sulfur. So you want to, more difficult means that you need the higher pressure, higher temperature to treat thiophenes. And nitrogen, oxygen, olefins are easily transformed into stable paraffinic hydrocarbons because it's not only hydrotreating, but it is also hydrogenation. You add the hydrogen and you have the olefin. Of course, the olefins will be hydrogenated into paraffinic hydrocarbons. What are the olefins? Alkenes and paraffinic alkanes. And the metals compounds that contain these metals are destroyed and the metals get deposited on the hydrotreating catalyst. So the metals are deposited on the catalyst. That's how you remove the metals. What happens to sulfur? When you hydrotreat, what do you produce?
Hydrogen sulfide.
Exactly. With nitrogen?
NH3. Ammonia, yes. Ammonia.
Yes. And oxygen? H2 plus O2.
Water.
Yes. So sulfur, nitrogen, oxygen are converted to oxides. Olefins, so we have the hydrogenation reactions. Olefins are converted to paraffins, and metals deposit on the. So we have the desulfurization reaction, we have the denitrification reaction, we have the hydrogenation reaction, and we have the oxygen removal. These are the list of the reactions. In hydroprocessing, we have the hydrotreating and hydrocracking. During hydrotreating, sulfur and nitrogen concentration in the final product is reduced along with the saturation of olefins aromatics. So, the sulfur and nitrogen, it is first hydrocracked into the smaller molecule numbers of the hydrocarbons. Then hydrogenation happens to produce the hydrocarbons with smaller amount of the carbons. This is for hydrocracking. But in hydrotreating, directly sulfur and NH3 is the hydrogenated and is separated as the NH3 and or H2S. So hydrotreating, we have the liquid feed. We have the H2 makeup. Why makeup? We will see that we use the excess amount of hydrogen, then the rest is recycled. It is preheated. It is sent to the furnace. It is sent to the reactor. And after reaction, we use the heat of the products, which is the case for CCR, which was the case, to preheat the feed to the furnace. And then cooled the reactor products are cooled further and separated. You always have the separation and purification section after reaction. And then you separate the gases, you separate the liquids. Some of the gas, this is the hydrogen gas, recycled back to the system, and the some is purged. So we have the Nafta hydrotreating. HDS is the hydrodesulfurization. Kerosene, we mostly do not, nowadays, we don't use the hydrotreating for kerosene. We have the diesel, we have the VGO. And what we also had in the BFD, FCC, gasoline hydrotreatment. So chemistry of the hydrotreating, we use the catalyst. The catalyst is the cobalt molybdenum catalyst with on the aluminum bed. So you have the aluminum oxide as support, and you have the cobalt molybdenum catalyst. This is used mainly for the hydrotreating processes. So you have the hydrogenolysis, hydrodesulfurization, hydrodeoxygenation reaction, and also hydrodemetallization reaction. But as I said, metals mostly deposit on the catalyst. Inorganic sulfur is converted to H2S. The organic sulfur compounds are these ones, and the unification reactions also take place during the hydrotreating processes. I would like to skip this one, and now let's talk about the hydrotreating process conditions. So feed is mixed with the mixing point. Feed is mixed with the hydrogen, and then it is sent to reactor. And for instance, the C3H6 plus H2, we produce C3H8. This is composition reaction. Composition reactions are exothermic. So you can say that hydrotreating process is an exothermic process, which means that it is really essential to control the temperature in the reactor. And this heat exchanger and this one is the same, because here you cool down your product, here you heat your feed. And I told you the catalyst, cobalt molybdenum catalysts are used for sulfur removal. You can also use a nickel molybdenum catalyst for nitrogen removal. The pressure can be between the 300 430. So for instance, if the inlet is 400 degrees Celsius, the outlet will be 430 degrees Celsius because of the exothermic reaction. And the pressure is between the 7 and 180 bar. It is mostly around the 50 bar in our refinery, at Baku our refinery. And feed is mixed with recycled stream, sent to heat exchange, and in the furnace for heating the same. Eventually, the heated feed mixture is sent to the hydrotreating packed bed reactor. So, if you see something like this, this is packed bed. And this is a one reactor. It has one packed bed reactor. So for CCR and FCC, we had the regeneration of the catalyst, and we had the continuous catalyst regeneration for each of the process. But here we have one reactor without any regeneration. So this is the difference between the reactor in this process, the and other processes. Lifetime can be up to 5 years. So it means that once you fill the catalyst, if you keep the required operating conditions, the temperature and pressure, you can use the same catalyst for up to 5 years without change. However, if you, let's say, exceed the higher temperature, what will happen when you have higher temperature? You will have cracking. When you have cracking, you will have the coke formation, more coke formation. What will happen? Deactivating your catalyst, and then when your catalyst deactivates in a higher rate, so lifetime will be lower. And then after the reaction, you cool it down, and then you send it to the separator. This is the separator. You can also call it HP separator, high pressure separator, where the hydrogen is recycled back to the system, and sour water is separated. This is the three-phase separator, and then the liquid product is sent to the stabilization section. In the stabilization section, you again treat your product, you separate the gases, and then the sulfurized product, which can be different for each unit. For naphtha hydrotreating unit, this product will be naphtha. For diesel hydrotreating unit, it will be diesel product. And here, this is the secondary processes in the refinery. Secondary processes, which we will not talk about during this course. It is the amine treatment. What happens here? You have the gas from bottom, it goes up, and lean amine is fed to the column. Lean amine dissolves the H2S, and then leaves the column. And the treated, let's say, gas leaves the column from top. Rich amine is sent to amine regeneration, where the H2S is removed from amine, and then again the lean amine is sent back to the process. The gas stream emanating from the phase separator consists of the 60-90% H2. So here the gas is mostly H2. And the majority of this stream is recycled using a compressor to mix with the makeup hydrogen. When high sulfur feeds are used, H2S removal is carried out by placing an additional absorber unit with an amine as absorbent. So it means that if you have the too high H2S sulfur in your product, you have this H2S removal column. But if you see that sulfur content is not that much in the feed, then you don't need the H2S removal column. So this is again the typical scheme, the same scheme that we talked about. We have feed pump, we have the makeup hydrogen, feed preheat heat exchanger, fire heater, then it is sent to fixed bed reactor. In the fixed bed reactor, you have the product, heats the feed, and then goes to the cooler. CW is the cooling water. You use the cooling water, and it is sent to gas separator, where you have the gases, and then gases is sent to amine contactor. Sometimes it is not needed, so it depends on the H2S limit in the gases, and it is sent to recycle gas compressor. So The hydrotreating processes has two compressors. One is the recycle gas compressor, and the second one is makeup gas compressor or MAG compressor. So we have the recycle and we have the makeup gas. So if we have a block flow, we have the makeup gas, we have feed, and we have the reaction here. So the amount of H2 used in the reaction is this amount added to the system as a makeup gas hydrogen. The amount is exceeds, so you need, let's say, 1 mole hydrogen, but instead of 1 mole you use the 4 H2, then 3 H2 is recycled. Here also H2 to feed ratio is important, because as high as it is, you have better process. So sometimes you might have the 4 to 1. Normally you need 1 to 1, but mostly you have the 4 to 1. Then more hydrogen you have, then you use the bigger reactor, but you have the better process. That's why you have to see what are the pros and cons, where you have the lower cost and at which point it adds the costs, then you stop this ratio. For instance, you can go to 4, 5, 6, but when you go to 10, you will see that you need much bigger reactor. That's why you don't go there. So various sections in the Nafta hydrotreatment units are the charge heater, reaction section. So you have heater, you have reaction, you have stripping section, stripping reboiler. So heater, you have the reactor, and then the high temperature flash, low temperature flash. So flash means the separator, and LP separator, and then the flue gases leaves, and you have the stripper, or for where you separate the gases from the product. As you can see, H2 to hydrocarbon ratio is important for hydrotreatment processes. Now here in the upcoming slides, the hydrotreating Nafta unit process is explained in detail for each type of for each section of the, let's say, PFD. I will skip this one. I explained it in general, and after this one, I will explain the hydrotreating of diesel, which is similar process. Just what I want to show that here for hydrotreating naphtha process, we have the one bed reactor. Now, when we go to the diesel hydrotreating process, we will see that we don't have one packed reactor. Instead, we have 3 packed reactors. That's why there are some more quenching here, which I want to show you. I will skip naphtha hydrotreating. Now, the gasoline hydrotreating. For gasoline hydrotreating, I think I need to go to PFD. Yes. So diesel hydrotreater. Diesel hydrotreater or gas oil. You have the diesel oil from CDU. You also have the FCC gas oil. This fuel oil can also be sent to diesel hydrotreater. Sometimes you have the coker gas oil. This is also sent to diesel hydrotreater. So all the, let's say, the diesel you produce, you have in the different units of the refinery are collected and sent to diesel hydrotreater. For instance, now we have the modernization project in the Howard refinery, the hydraulic oil refinery. Diesel hydrotreating unit is the main unit of the project. Produce the Euro 5, the diesel. So Euro 5 diesel means that you have maximum 10 ppm sulfur in the diesel. This is the PFD process flow diagram of the process. I will talk about in detail. First, see what are our feed. Straight run diesel. What is straight run? SR. SR means that diesel from CDU. So secondary units, FCC, from diesel from FCC and diesel from DCU, delayed coker, DCU. So we mostly improve the product quality is within the respect to sulfur and condensated carbon. Condensated carbon kind of the residue in the products. Until a few years ago, 1% sulfur was acceptable, 1% sulfur. But now it is, 10 ppm. 10 ppm is 0.001%. So because of the global warming and environmental pollution, there are always more restriction coming to the fuel impurities such as sulfur and nitrogen. So this is a 0.005. This is a 50 ppm, which is a standard for Euro 4. But Euro 5, it is 10 ppm. Let's start from the beginning. This is the same as what I explained in general for hydrotreating processes, but I will explain it again so that it will be repetition for you. We start from the feed. Feed is pumped in a liquid, and we have the preheat exchangers. So feed is coming from here. It goes to the first preheat exchanger, and then it goes to the second preheat exchanger, and then it goes to the reactor. So the feed with the mixes with the hydrogen. It's something. Something wrong actually in this scheme, because feed should come from here, or anyway, the feed should come from here, from the heater, because we want to heat until around the 400 degrees Celsius, and then this should be the hydrogen. It mixes with the hydrogen and it is sent to the reactor from top. As you can see, we have the first bed, second bed, and third bed. And this is the hydrogen. This is hydrogen. Hydrogen is mixed with the feed, and also it is used for quenching. Quenching means the cooling. It can be sent to in between the packed beds, between the first and second one, and also the second one and third one. And the question, why we use the hydrogen as quenching in between the first and second, and the second and third reaction zones? Why do you think we need the hydrogen to quench or to cool down the stream between the reaction zones? What type of reaction we have in hydrotreating? Exothermic or endothermic?
Exothermic. Exothermic.
Exactly. What happens when we have the exothermic reaction?
Heat will be released.
Produce heat.
Yes, temperature increases. So let's say we have the 400 here, we have the 430 here. And more reaction means more heat. If you have one single bed, it will be really, really difficult to control the temperature here. It will go up to 500 degrees Celsius. And we don't want that one. Why? Because if we have really high temperature, we will have the hydrocracking reactions. The first. And secondly, we need the reactor to withstand much higher temperatures. That's why if you have 430 degrees Celsius here, we add the hydrogen quenching here to bring the temperature down. I don't know, maybe 415, something like that. And again, we have the increasing temperature at the outlet of the second bed. Again, we add the hydrogen quench, and then it leaves the reactor with higher temperature. So hydrogen quenching is essential to control the temperature. Once it leaves the reactor, it is pre-feed heat exchanger where we pre-feed our inlet. So this is our product. Goes like this one. So we use the heat from product to heat the feed. So this is also a HEN, heat exchanger network. We have heat exchanger network at each unit. Everywhere we have it. This is the heater. Yes, please.
Sanan Bey, please consider the time is limited. It's already 1 hour and 40 minutes.
Okay. So this is okay if I finish in 10 minutes?
Yeah, okay.
Okay, thank you. We have the heater here and we have the compressor. Again, we have the recycled gas compressor. Yeah, we don't have makeup gas compressor here, but we have in the unit, not shown here. And in the reactor, cobalt molybdenum catalyst is used, or nickel molybdenum. We said the cobalt molybdenum is mostly for sulfur removal, nickel for nitrogen removal. And we have the 3-bed reactor here. This is the heat exchanger network. And we have the condensate. The condensate is injected into the reactor effluent, so to the product. So this is the product just before air cooler. Dissolution and removal of ammonium salts. So we add the kind of the water to dissolve the ammonium salts. Then we cool it and send to high pressure separator. In high pressure separator, we separate hydrogen, and then it is sent to 3-phase separator. Here we have the water. Here, this is our main product. This is the gases. High pressure separator, and then the hydrogen is separated from HP separator, sent to compressing section. We use the solution to treat the gases. So gases plus DIA. We clean gases from H2S. So DIA, sometimes MDIA, diethanolamine or methyl diethyl dissolves or absorbs H2S. So make up hydrogen, I talked about the previously, and this is the HDS, means that hydrodesulfurization, three-phase separator, I talked it, and this is the stabilizer column. After each reaction, we have the stabilizing section, and in diesel hydrotreater, what we do? We separate the gas, we separate the naphtha, which is in the diesel, and we separate the diesel product. This is directly sent to sales. But this naphtha is still unstabilized naphtha. This naphtha is sent to CDU, crude distillation unit, recycled back to the beginning of the process. So this is the reflux from where some of the naphtha is sent back to the column top as reflux to control the temperature here. And the product is sent to the air cooler and cooling water cooler, and final product is sent to the storage. This is the PFT catalytic. So what I want to show that we had the distillation steps. We said that we saw the desulfurization, reforming, desulfurization, and catalytic cracking. So in this the course, we learned about the CDU in detail, VDU, hydrotreaters, not Merox, hydrotreaters. We learned about the FCC. We learned about the catalytic reformer. Thank you for your attention. Still, the refinery processes are a lot. Hopefully, next year we might have an extended refinery course to talk about the other refinery processes as well, such as the sulfur production, the hydrocracking, alkylation, the MTBE, methyl tertbutyl ether production, etc. Now, I want to the quiz questions to you.
Thank you very much, Sanan Bey, for such an insightful presentation.
So, let me find chat. So, also organizers, Kafya Hanım, Talya Hanım, they don't know, they didn't see the questions. That's why feel free to attend the quiz and to earn the gift. I sent the link to you. Please write your name, surname, and email quickly. You will find the questions there. You can finish the questions in 10 to 15 minutes, I think. Of course, who has the highest number of the correct answers will be the winner. If there are 2 or more people with the same correct answers, then I will check the submission time. I think everyone can see the quiz. So you have 10 or maximum 15 minutes to finalize the quiz. Nijat and Rodrigo have already left, but if you are done, please don't leave because I will announce the winner and what the gift is immediately. Please finalize it in 3 minutes.
Sanan Bey, can I ask one thing?
Yes, sure.
In the questions, it was FCC products are, I think it should be not multiple, it should be open-ended questions and we can click some of them. At least 3, I know.
But in the end, there should be answer like
Only one or all, okay.
So please finalize the quiz. Let's say 1 more minute. Then I will announce who the winner is. Okay, now I would like to share the should I do that? Should I share the screen? Okay, I will. If no one hesitates, I want to share screen and everyone see everyone's results. Is it okay? Or someone does not want it?
Say the winner only.
Okay, winner only. We have 21 out of 25, and we have 19, and we have 18, so close. But the one who has 21 is Afak Hashimova. Congratulations to Afak Hashimova.
Congratulations, Afak.
Thank you.
So maybe you can introduce yourself, where you are studying, and
I am Afak Hashimova, and I am studying in Bakü Oil School, third year chemical engineering student.
okay.
But
Nice.
I don't want to talk too much about myself, but about you, because, for example, in this process engineering course, the most intriguing and the most, I think, the insightful sessions were yours. I really enjoyed your sessions, and I want to thank you for such a great sessions, and I would like to see you in the next webinars also.
Thank you, Afak, for your kind words. I also enjoyed the today's, not today's, the general the sessions with you, because you and also others were quite active during the sessions, and I think that also made the course interesting to me. And finally, I would like to show this is your gift. This is the thermo cup of the Sokar downstream company, which is now the responsible for the refinery operations at the refinery. And now I am in my hometown. Once I am back to Baku, I will contact the organizers, and I hope they will help me to deliver this gift to you.
Sanan Bey, I would like to also add one more thing, that Afak is also one of the organizers of this process engineering course. She's also working in SPE BHOS team. Yes, you can also contact with her.
Okay, perfect. Then I will contact her, and I will deliver this gift to you. Yes, that's the end of our session, and I believe that is the end of the process engineering course. I would like to thank all the organizers, especially for organizing such the long-term course. I also worked in organizations like you when I was a student, and I believe that it's not easy to organize even one session, even one training, but you did a great job. You invited the 7 speakers, and it lasted for 6 weeks. Maybe in total there were more than 20 sessions. So good job. Congratulations to all the organizers. And I would like to also thank all the attendances. I believe you earned some knowledge from my sessions and as well as the other sessions. This knowledge will be useful and helpful for in your future. I will also add the email in the chat session, and I will share all the presentations with you. So if you have any questions regarding this session, oil processes, or in general about the chemical engineering, please do not hesitate to contact me, to ask your questions, to have discussions with me.
Thank you very much, Sanan Bey. And as you know, today is the last day of the process engineering course, and we had the last session with you. And I wanted to say huge thanks to our dear participants who participated during in the sessions. I believe and hope you have learned a lot of new information from our dear speakers.
Thank you very much, Sanan Bey. I think it's all for today, but we'll again meet in the next upcoming sections and also in the next academic year.
Thank you very much.
Thank you.
Thank you so much, Sanan Bey.